In the My Game folder, there's a folder called App, which contains the main.rb file that we are using. We have a Dragon Ruby window on the left and a VS Code window on the right, but you can use any text editor. We have a blank screen, but we want to make the screen a different color. First, type args, which is short for arguments, dot outputs. Computers have inputs and outputs, so this is an output, dot solids, as in a solid color. Two less than signs represent the concatenation symbol for Ruby, and we will have a list of 4 parameters. The list will have the X and the Y positions for the object we're making, and the width and height of our new object, 1280 pixels across and 720 pixels up and down. When you save the file, you should see a black screen come up. If you remove a parentheses and save the file again, Dragon Ruby will tell you that you have an error. In this example, our error is a syntax error, and it is expecting a closing parentheses. When you add the parentheses back and save the file, Dragon Ruby's error message will go away. What we want to do next is create another solid in the center of our black screen. Again, we'll type in args.outputs.solids with the concatenation symbol, but this time we will have a few more parameters. Everything in Dragon Ruby is based on 1280 and 720. In order to put something in the center of the screen, we will divide those numbers by 2 to find our X and Y positions. The next 2 parameters are the width and height of our object. In this case, we'll do 30 and 30. And the next 3 parameters are for the red, green, and blue saturations. We will write 255 for each of these. When you save the file, you should see a white box in the center of the screen. If you change the width value, the shape will change accordingly. The same applies if you change the height value. The red, green, and blue saturations are all based on hexadecimal values and can be any number between 0 and 255. If you change the green and blue saturations to 0 while leaving the red saturation at 255, the square will turn red. You can manipulate these numbers to get the color that you want. What we want to do next is make the square move on the screen. There is another property on args called state. It is known as the Magic Data Structure, or MDS. Everything about your game, meaning its properties, data, etc., goes on state, and it can accept any property that you give it. The pipes in front of the equal sign mean only set the value of x equal to 640 if the value of x has not already been set. The same applies to y. Only set the value of y equal to 360 if the value of y has never been set. In the parameter list we use to create the square, we're going to replace the 640 and 360 with the x and y that we just created. So replace 640 and 360 with args.state.x and args.state.y. In order to make the square move, the x and y values must be manipulated, so we will add 1 to each of these values. args.state.x plus equals 1 will increase the value of x by 1. We will do the same thing to args.state.y. We will add 1. When we save the file, the square should begin to move. Once the square goes beyond the scope of our screen, how can we make it wrap back around? To solve this problem, we will need to use an if statement. We will set the value of args.state.x equal to 0 if the value of args.state.x exceeds the width of the screen, which in this case is 1280. Next, we will set the value of args.state.y equal to 0 if the value of args.state.y exceeds the height of the screen, which in this case is 720. Doing this will send the square to the lower left corner of the screen every time it exceeds our scope. You can manipulate the speed to make the square move faster or slower by changing the value that is being added to x and y. This method is beginning to look really big. In order to make it more manageable and easier to understand, we're going to break it up into 3 different methods. These methods will be called defaults, render, and calc. The defaults method will be used to set default values. Render will be used to make solid objects. Calc will be used to manipulate the square object and make it move across the screen. Any code that does these things will be moved into the appropriate method. In tick, we must now call all the methods that we just created. Tick sets defaults, renders, and calculates constantly, over and over again. When these changes are made and the file is saved, everything should behave the exact same way, but the code is now easier to understand and follow. What do we do if we want to make multiple square objects on the screen wrapping around? We have to use an array. We will create a game state that is a list called stars. args.state.stars. Arrays and numbers both have maps, so we will use a map to create, in this case, 10 stars. We want to give each star a random starting position on the screen, so we will set the x and y values by multiplying 1280 times rand, which is short for random, and 720 by rand. The render method will be changed as well. The first line of render, which sets the black screen, will remain the same. Then the second line, we will use plus equals instead of concatenation, since there is more than one item in this map. Using a map means do the specific thing or perform this action for every list item in the collection, which in this case is our 10 stars. We will put x and y inside of the pipes. For every star, we will have the x and the y position, set a width and a height for the stars, in this case both values will be 30, and a color using the red, green, and blue saturations. Next, we're going to update the calc method with map again, so every star can move across the screen. We're going to put x and y inside of the pipes, and we can now remove any repetition inside of the method by changing every args.state.x to just simply x, and every args.state.y to just simply y. We must send the star back so it can appear on the screen, so xy returns the star. Pay special attention to the fact that every do is accompanied by an end. When you save the file, you should see 10 stars floating around on your screen. We want to make the stars a little more unique. They each have a random x and y position, but now we're going to include 10 times rand plus 1 in order to give each star a different speed. We will multiply 255 by rand for the red, green, and blue saturations in order to give each star a random color. There is a data structure in outputs called sprites. Sprite is a computer graphics term, and they are often used in games. In the render function, we will be replacing our previous solid with sprites, and we will also be adding a few more values inside of the pipes. Inside of the parentheses, we will have the x and the y positions, the width and height, the location of the sprite, or where the .png file for the image itself can be found, the rotation of 0. Since the objects are squares, a 90-degree rotation would not make a difference, the opacity, and the red, green, and blue. The sprites PNG that we just used is in a folder called sprites, which is a sibling to the app folder found in my game. The calc method will also be changed, and more values will be added inside of the pipes, including the speed, red, green, and blue. The x and y values, instead of adding 1, will now add the speed so that each star will move at a different speed. We will return the x and the y positions, the speed of the star, and the red, green, and blue value for each star. If you save the file, Dragon Ruby's console will appear, and you will have to type $dragon.reset in order to restart your game. You can access the console at any time by pressing the tick key on your keyboard above the tab key. Any method in your program will work in the console. So if we create a method called R that holds $dragon.reset, we can avoid typing this command every time we wish to restart our game. The best way to create any game is to make small changes to get to the next point of complexity. Start with one large method, break it down, get an idea of what the game will look like, and then add visuals. What we'll do next is add a sun to our solar system. To do this, we will declare the sun as a new entity inside of the defaults method, write do, and put s inside of the pipes. We will now set the default values for the sun. The sun's path, or the location of the sun's.png file, is in the sprites folder and is called sun.png. The sun's x and y values will be 640 and 360, and the size of the sun, or S, will be 100. We also want to create planets for the solar system using an array. The array will contain the name of each planet, the distance of each planet from the sun, and the size of that planet. All of these planets will be in a map, and we will put name, distance, and size inside of the pipes. Each planet will be declared as a new entity. We will set the path for each planet first. The PNG files for all of the planets are found in the sprites folder, but are named individually based on the planet's name. The x value of each planet will be equal to the sun's x value plus the distance of that planet from the sun. The y value will remain 360 for all of the planets, so each planet will be displayed in a straight line. S will be equal to each planet's size, and these values can be found in the array. We are going to create a new method called toSprite, and this method will take entity as a parameter. Entity could possibly refer to the planets or the sun, etc., and this method is involved in the placement of the entities on the screen. We must output the newly created entities so that they appear on the screen. To do this, we must alter the render method. Since the sun is a sprite, we will type args.outputs.sprites and use the concatenation symbol since there is only one sun, and call the toSprite method on the sun. Next, we will output the planets as well by using a map. Since the planets are also sprites, we will type args.outputs.sprites, but use the plus equal signs this time because there is more than one planet. We will then call the toSprite method on the planets. If you save the file, you should see the sun in the center of the screen and the rest of the planets that we just added. Moving forward, we're going to change the defaults method by getting rid of the x value and the y value for the sun. We'll address these values later. If we want to make the planets orbit around the sun, we're going to have to add more information about the planets inside of the array. And what we're adding is the number of days that make up one single year or orbit around the sun. For example, Earth's year in days value is 365 because there are 365 days in one single year. We'll add this new description, year in days, inside of the pipes. We're going to remove the x value and the y value for the planets, similar to how we got rid of them for the sun, but we'll be including the new values that have been added. p.distance will be equal to the planet's distance from the sun, which is found in the array. p.year-in-days will be equal to each planet's year-in-days value, which is also found in the array. The toSprite method will now have two parameters instead of one, args and entity, and here is where we will set both the x and the y values equal to 0. If the entity's year-in-days value is not nil or unavailable, we'll do the following by using an if statement. 1 day will be equal to the tick count. Day in year will be the day modulus year in days. For example, 30 mod 365 is 30, so it would be the 30th day of an Earth year. Percentage of year is the day in year value divided by, using fdiv which uses floats, the year in days or number of days that make up one single year. Day 30 divided by 365 days would mean that 8% of the year has passed. Angle will be 365 times the percentage of year value. X is equal to angle.vector x with entity.distance inside of the parentheses. Y is equal to angle.vector y with entity.distance inside of the parentheses again. After we're done with the if statement, we're going to change the values inside of the parentheses that set the x and y positions, the size, and the path of the entities. Instead of entity.x and entity.y, we will now have 640 plus x and 360 plus y. When we call the toSprite method inside of the render method, we must remember that we changed the parameter list for toSprite to args and entity, so we'll change the call to toSprite for the sun and planets accordingly. If you save the file, you'll see the stars, the sun, and the planets. Each frame is equal to 1 day, so after 365 frames, the Earth will return to its original position. You'll notice that Jupiter's one orbit around the Sun is equal to around 12 years. If you watch the Earth and Jupiter move, you'll see that you have almost a clock in the solar system, with Earth as the minute hand and Jupiter as the hour hand. As nice as it is to watch the solar system we've created, we do want to make the game interactive. Let's add a little spaceship so we can fly around in space. In the defaults method, we're going to declare a spaceship as a new entity and set some default values for it. The x value and the y value will be random, so that the ship can appear anywhere within the 1280 and 720 screen range each time the game is reset. The angle of the ship will be set to 0. In the render method, we'll output the ship so it appears on the screen. The ship is a sprite, so we'll write args.outputs.sprites with the concatenation symbol since there is only one ship. The list will have 5 parameters: the x value of the ship, the y value of the ship, the width and the height of the ship, the path of the ship or where the .png file for the ship is found in the sprites folder, and the angle of the ship. If we're going to make the ship move around the screen, we'll have to make a new method to process input from the user. We will name this new method processInputs. Inside of the method, we will use an if statement. If the user presses the left arrow key on their keyboard, the angle of the spaceship will increase by 1. Else if the user presses the right arrow key on their keyboard instead, the angle of the spaceship will decrease by 1. We can add another if statement to this method as well that says that if the user presses the up arrow key on their keyboard, the change in the angle will be added to the x and y values of the ship. Make sure you add this new method, the processInputs method, to tick so that the user's inputs can be processed. When we save the file, we should see the spaceship on the screen. We can now move the spaceship in any direction we want and make it fly around in space. In order to give our game a more extraterrestrial feel, we will also be adding music to the game as another feature. We will say args.outputs.sounds with the concatenation symbol. The file we want is found in the sounds folder, which is a sibling to the sprites and app folders, and the file is called bg.wave because it is a wave file. Keyboards are not the only source of input that can be used. We can also have remote controllers. In the processInputs method, we can add code so that if the user presses left on their remote controller, the result will be the same as if they had pressed the left key on a keyboard. The same applies to pressing right on their remote controller. We will add an OR to the if statement we created originally to do this. If the user holds the up key on their controller, the spaceship will behave the same way as if they had pressed the up key on their keyboard. Again, we will add an OR to the if statement in order to do this. When you save the file, after all of the changes that we have made, Dragon Ruby's console should pop up. Type R in order to reset the game. You should now hear music and should be able to fly your spaceship around in space.